The next query that we're going to analyze with Visual Explain is this select. It has 4 columns from the bank.history table, a predicate of teller ID equals 200. So since there are 1,000 different teller IDs, this will be one of the 1,000 tellers. There's an order by account ID, so when it retrieves these transactions, it's going to sort them by account ID before the result is returned. We could run the query and actually see the result. We're going to run Visual Explain just to look at the access plan. We have a number of settings we could choose. For example, we could set a schema if we had unqualified tables. We're going to take all the defaults. The access plan appears here as the access plan diagram. We will maximize that to make it easier to look at. A quick review of the access plan. The return shows a estimated cost of $22.40. Processing begins here. There's the icon that shows an index, the icon that shows the table. We have the index scan operation, so access to the index, the fetch operation, the access to the table, the sort, and we had an order by clause, so we have a sort operation. Table scan is to retrieve the sorted result and then return the result of the application. So total estimated cost of $22.40. We'll start here looking at the index that was chosen. Over here on the left, we have information about the index. The index was defined with 2 key columns, the first column being branch ID, second column being teller ID. So since we have a predicate on teller ID, the index has some use. First operation here in the access plan is the index scan. So when we come over here and look at information about the index scan, we have the detailed information. It shows the estimated cardinality is about 200, 198. There are 200,000 rows in the table, so picking one of the 1,000 tellers is estimating about 0.1% will match that predicate. We have the total cost of $7.43 for the index scan, an I/O cost of $5.39. So, we're going at 1 teller out of 1,000 tellers. Seeing an I/O cost of $5.39, that's 539 pages referenced by the index scan. So that seems to be quite large. When we look at the predicate that's being used for the index scan, well, it's the teller ID equals 200. We have the filter factor here, showing how many are going to match. So it's just under 1 per 1,000. The type of predicate it shows as a sargable predicate. That means that as it scans the index, so it'll be a complete index scan where it will actually look at the second column in the index to see if the teller matches. So it's not a very efficient use of an index to find the matching rows. Now, once it has the result from the index scan, the 200 entries, it's going to fetch those rows from the table. So the next operation is the fetch. When we look at the fetch statistics, shows now a cumulative total cost, which includes the index scan, is now up to $22.40. I/O cost of $7.37. So it seems that of the 200 rows we're looking for, that almost all of those will be in different pages. So those 200 rows are scattered all over the table, so quite a lot of IOs to actually fetch the data, and therefore quite a lot of extra cost. Now at this point we're at a cost of $22.40, which is almost all the cost of this access plan. So it says that the sort operation and the table scan don't add much additional cost, but this is $22.40 to retrieve the 200 rows, sort them, and return a result to the application. To compare this, we have another table that we can use. History CP was loaded with exactly the same 200,000 rows, but its characteristics are a little different. One thing is that it was defined with adaptive compression, so the 200,000 rows fit into a much physically smaller table with fewer pages. Also, what's important is this table has two indexes defined, one specifically on branch ID and one on teller ID. So we'll see how that impacts our access plan. We'll now explain this, again taking the defaults for the explain processing. We will maximize the access plan. Now operation-wise, it looks similar. We have an index scan, the fetch, the sort, the table scan, and the return. The icon here shows which index is going to be used. When we look at this index and look at the index keys, we see that it has a single column used for the index. It's teller ID. Now, here when we look at the return, we can see that overall the access plan, the estimated cost, is under 26. So this was compared to 2,200. So it's roughly 1% of the cost of the other access plan. The index scan here has an estimated cost of 15, and when we can look at its characteristics. It has two predicates. It has a start key predicate of teller equals 200. Because we're looking for just a single teller value, that is also the stop key predicate. So it's a very narrow range of the index. When we look at the costs of the index scan, we have this roughly the same estimated cardinality, 199, so just under 200. We can see the total cost of 15, the I/O cost of 2. So now, instead of being 500 pages being read as part of the index scan, it's estimating 2. We can look at the other characteristics of the index. And one important element here, data clustering is at 1, which essentially means 100%. So it turns out that this table was reorganized with the reorg utility with this particular index being referenced. So the reorg utility arranged this table to perfectly match this index. And that's going to have a big impact, so we have a cost of 15 for the index scan. When we look at the fetch operation, the estimated cost now is a little over 25. Remember, it was 2,200 before. That includes the cost of the index scan. So again, the estimated cardinality is 199, total cost of 25, so a little less than 26. The I/O cost is 3.3. So that tells us that including the 2 I/Os from the index scan, that there's 1 or 2 I/Os being required to perform the fetch of the 200 rows. Because the data is so clustered, that just a small number of pages will actually hold all the information we need. So again, we follow by the sort and the table scan with the overall cost here of under 26 compared to 2200 using the alternate table to perform the same query and return the same result. So dramatically more efficient to use this version of the table, both being compressed, having the appropriate indexes, and actually being reorganized to match the index that we are using for this particular query.